Okay, so before the break we were looking at functions which took I/O things as their arguments or part of their arguments. And we looked at, in particular, a function which took an instruction to produce an A and turned it into an instruction for producing a pair of A's, and it did so by running the instruction twice inside a do block. Now there are some standard functions which are very useful, which are worth seeing the definition of. One of which is the function sequence, which takes a list of instructions and runs them all one after the other. In other words, it creates a new instruction by running each of the individual instructions in the list. But it doesn't return any particular result, so it doesn't care about what values are produced by the instructions you run. So if we take an example, there's a function print which takes anything which is showable, anything which you can convert to a string, and sends it to the standard output. So it turns a thing into an instruction for displaying one of those things on the standard output. So if we, for example, print 42, it will print the value of the thing that we ask it to do. If we ask it to print something which is not showable, for example, a function, then it says, I don't know how to show something of this type. Okay, but anyway, it's just something we can use in small examples. So, for example, if we have a list with two instructions, that's a list which is I/O of whatever, I/O of nothing in particular. We can run sequence on that in order to produce, in order to run the first instruction and then run the second instruction. So we could have used sequence to, well, okay. So what's the definition of sequence? Well, let's define our own version. We'll give it this specific type. And how are we going to do it? Well, we're going to use recursion over the list argument. The base case being when you want to do a sequence of no arguments at all. So what I/O result should I return in that case? I'm going to return unit. Do the trivial computation. Otherwise, if it's an instruction followed by another bunch of instructions, then I'm going to do recursion by using a do block, and inside the do block I will, let me start the whole thing on the next line. I'm going to run the instruction I, and then I'm going to recursively run the rest of the instructions. And that's the definition. Okay? Any questions about that? Okay, now it turns out that, in fact, this do notation is actually just syntactic sugar. It's actually not, it's just an extra bit of syntax that Haskell adds to something which is built on top of more primitive operations. And when you want to do something of type I/O something, ignore the result and then do something else, then actually there's an operator, which is this one here. So this would have been equivalent to writing, instead of a do block, I followed by my sequence is. We could have written that instead of the do block. And then you could see, in fact, what we could have done is use what kind of function. What we're doing is combining all the elements of this list using a combining operator and a base case. What function do we use for that? Combining function.
think that we can write my sequence equal the operator?
No, the operator just applies one I/O thing and another I/O thing to get the third I/O thing. We need to do it between every element of the list. Nobody remembers the function, the pattern, the computation pattern for combining the elements of a list? It wasn't map. Map is a computation pattern for applying something to every element of a list. What was the computation pattern for combining the elements of a list? Fold. We had functions fold R. So this would be fold R with this operator and this base case. All right. I think you need to go back and have a look at fold R. What about this guy here? This is very similar, a little bit more complicated. The base case, in this case, we need to return a list of A's. So if we've got no instructions to compute, what list of A's can we return? Well, we can return the empty list. Otherwise, if we have an instruction followed by some other instructions, then the result will be what we get by doing a do. We compute the instruction, but we want to actually save the result. And then what do we want to do? Well, we also want to compute my sequence of the rest of the list. That's all very well, but we actually want to save that result as well, call that A2. The reason is because what we want to return as the result of the whole thing will be A1. Oh, well, let's call that A's. There's more than one A there, and there's a single A there. We're going to return the A followed by the A's. Okay? So this is the thing which takes a list of instructions for producing A and turns it into one single instruction for producing a list of A's. Okay? All right, with those examples, then you might like to, at some point, return to these examples and see if you can define the functions specified in this example. So one is to copy all the contents of all the files together, join them all together into a single, and put them into a single file. And the other one is a sort of for loop. Okay, I'll leave that as an exercise. Any questions? Okay, what I want to do in the rest of the lecture is one final example, and it's a standalone example. Let me just compile this. So here's a program that I'm compiling. So I'm compiling it to a standalone instruction, which I can run. And it's the Hangman game, where you have a sequence of characters you've got to guess, and the characters form a word, in this case a dictionary word. So I can guess some characters. Let me guess S, T and E, the most popular letters, only it's got an E in it, and I've burnt two of my, or three of my lives there. Let me guess H, A, O, I, N maybe. T, oh, I've done T already. Okay, that didn't use up a guess. L, anybody? F's a good one. No, not so good. Z? You're kidding me. Oh, C, sorry. The word was in-rigged. One of those everyday words. Okay, so the task now is to actually define this thing, and I've got a file that I've started here, and it's not very big. So you notice that I compiled that into a standalone program. A standalone program in Haskell is the result of running a function called main. So if you want to have a standalone program that you can compile and run as a standalone program, it has to contain a function main, That will be the thing that's run. And the type of main will be something which has type IO of nothing. It doesn't produce any result. Its only job is to interact with the outside world. Okay, in this case, it's interacting with the dictionary file that's stored on the computer and me who is inputting characters. And then it outputs to the standard output. So no fancy graphics or anything, but it's a basic example of a program with I/O. This is where I got the dictionary on my computer. Of course, this is dependent on which machine you're on. There'll be something similar somewhere on a Linux system. I don't know about Windows where you would find something like this, but there's probably some list of words somewhere. And I've put in here, let's have a guess limit of 10 guesses, or 12, whatever, it doesn't matter, not too important. I'm predicting I'm going to use some functions from the list collection. I've already imported those. So let's actually start defining this thing. So what is this main going to do? Well, it's a game that consists of picking a random word from the dictionary and then basically playing the game. Okay, so there are two phases to the game. Selection of the word and playing the game. Okay, so this is basically going to split our operation into two parts. We're going to select a word. Let's call that random word for the sake of argument. This is going to be an operation which will interact with the operating system to firstly get a source of randomness, and using that source of randomness, pick a random word from this dictionary. Okay, so there's various interactions going on. So this will be an I/O thing, but this will be an I/O thing that will result in a string. Okay, so this will result in a word. Let's call it W. So this is a computation we will define shortly for producing a random word. Now, given the random word, we're going to start playing the game. So a game is a repeated process, right? It's an iteration, it's a loop. Any game is a loop. What state do we need to know at any point in the game? At any point in the game, we need to know what the word is that we're trying to guess, and we need to know the sequence of characters that we've guessed so far. Okay? Given those two pieces of information, that's all we need to calculate everything we need to know and everything we need to display in the game. We can work out if we've got any lives left. We can work out what to display. So they're the two pieces of information that we need. So what I'm going to do then is run a game loop. And the game loop will maintain those two pieces of information, namely the word and the guesses so far. So how many guesses are there so far when we start the game? There are no guesses at all. I'm going to use a string to represent the characters that I've guessed so far. So the initial guess will be, the guesses so far when we begin the game will be the empty string. Okay? Okay, so random word will be something of type IO of string. That would generate the, let's just write in a random word function for now. Let's say that this is not so random. So there's the random word. I just randomly chose it, so it's pretty random. I'm not sure this game's ready for production yet, but we'll get there. And the game loop, what's the type of a game loop? Well, it takes the word and a string, which is the guesses so far, and does our I/O. Okay, so game loop is the main engine of the game. And what will the game loop look like? Well, it will have a word, and it will have a list of guesses that have been done so far. And there are three things that the game loop can do. It can decide you've won the game. Hooray. Fireworks. It can decide you've lost the game. Maybe it'll tell you what the word was, as it did in the example I just gave you. Or the third case is the case where we sort of really do the work, and that is where we get a new guess from the player. We show them the progress so far, and we continue the game. So there are three cases: winning, losing, and basically the rest, which is playing. Okay, so we can break that down into 3 cases. If we win, we're going to display some winning whatever. If we lose, we're going to show some losing stuff. Otherwise, we're going to actually play a round of the game. Okay, so all these are things which I haven't defined yet. I'm going to define them shortly. But they will all depend on W and G. They are all that I need to decide whether I've won or lost. Okay, in the case when I have not won and not lost yet, I've still got some guesses left. What am I going to do? Well, I'm going to display the status and then, so this is going to be a sequence of interactions. I'm going to display the status, start this down here. Then I'm going to get a word from the user. So let's say I get some guesses from the user. Where am I going to get the guesses from? I need some way of getting something from the input. There is a function called readLine. There's a function called getLine. I'll edit that out later. Which produces an IO string. So this gets the next line from the input stream. Okay. So it interacts with me and gets the next line that I type and returns that as a string. So I'm going to do a get line to get my next guess. And after I've done my next guess, I'm going to go continue with the game. And continuing the game means going back into the game loop with the same word, but now I have some more guesses as a first approximation of what we could do. We could add the guesses that we've just made to the guesses that we already had. Okay, let me just finish this, fill in this so we can actually run it. Let's just say we don't win or lose at the moment. We need to define show win. Let's make these all local definitions. That's rather important actually for the moment, so let's make this an aware. These are all local definitions. So why are local definitions important here? They're important because I'm going to use in the definition of these things the parameters W and G. Because these are all defined with one pattern, W and G, I can use W and G in the local definitions. So I don't have to pass them in as parameters. I'm going to show win. Okay. And show lose is also going to be undefined for the moment. Display status. Okay, let me just say just quickly, what is it? What do you, when you want to print something on the screen? If we want to display a string on the screen, there's a function to do that. We saw the function print, but actually print is defined in terms of some other functions, one of which is putstr. So what we're going to do is this function sends a string to the standard output and terminates it with a new line character. Putstrln just rolls off the tongue, doesn't it? Okay, I think we can actually run this. It's not going to do anything very interesting. I can type stuff. The word was zebra, so I could guess a Z. I could... Wasn't it? Oh. Okay, I can never win here because a win is always false. All right. Yeah. Can't do much testing yet. The program's a bit incomplete. Okay, any questions about the structure of the program so far? So we now need to fill some of this stuff in to make it actually work. Okay, where should we start? Let's start with, where should we start? What do you want to see?
The word I.
Which one, sorry?
The word I. Is it right after the I?
Oh, this one here, random word. Okay, so random word. We're going to read from our dictionary. Our dictionary was defined up here, the word file. So what we're going to do is we're going to get the word list. This is very similar to what we did before when we found the longest word in the dictionary. Here we're going to take the word list and we're going to choose a random word. So how are we going to do that? Well, what we need to do is we need to generate a random number which is somewhere in the range of between the first word and the last word, and then choose that element of the list. So if we can generate a number between 0 and the length of the word file roughly, and then grab the element which is in the word file at that position, then we've done our job. So what is the word file? Well, the word list is just a single string. We need to turn that into a sequence of words. So we can do that with the function words from the word list. That's fine. So this is the thing that we want to work with. Now, we maybe can give this a name, but this is not an I/O thing. This is not an I/O thing. So if we want to give this a name, we have to use a let. So this is a let in a do. We say let the words equals what we get by applying the words function to the word list. So this is a pure computation, doesn't involve any I/O. That's why it uses a let and an equals and not one of these things. Okay. So what are we going to do with our word list? Well, we need to randomly pick a word. Okay, so we need some random stuff. Okay, so where might we find some random stuff? Well, let's have a look at Hugel, see what Hugel says. Let's get lucky with a bit of random. There's a system.random collection, which is quite nice. And what we're going to use from that is a bunch of random stuff down here involving I/O. This is the guy that we're going to use. So this is a class of things that can be randomly generated, but we're just going to use numbers. You give it a range as its argument, and it will generate a random thing in that range. How does it actually do it? Well, the runtime system has a random generator built in. So this is consulting, that this is using the built-in random generator that is inside the I/O and using that to generate a random value. That random value, notice, is always wrapped with I/O, because the only way we can get a random value is to interact with the runtime system. We're interacting with the outside world to get a random value. Otherwise, we'd get the same value every time if we had a pure function. That cannot be a pure function. So this is the guy we're going to use, RAO. So what we're going to do is we're going to get a number from this RAO with range, and it's going to be in the range roughly 1 to length of the word list. Sorry, length of WS. And then what we need to do is we need to take this word list and choose the nth element of the list. Okay? How do we do that? How do we choose the nth element of a list? Good question. We can ask Hugel. If we have an int and we have a list of A's and we want the 8th element, we're going to expect something of that type. What might have that type? Well, actually the first hit is the one that we want. It's the list index operator. It's an operator which gives us the element at that list starting from 0. So let me Control C this guy down here. If we have the list from 1 to 10 and we take the ninth element, that's the number 10. So we take the 0th element. The first element is number 2. We take the 10th element, we'll get an error. So what we want to do is to generate actually something in the range 0 to length minus 1. That's our... What did I do then? Did I delete a bunch of stuff? Getting too enthusiastic. So what I want to return is the word from the word list, which is at the nth position. So there's random word. Okay, that was a little bit... okay. Random... this random RIO, I need to import that, and that's from system.random, I believe it was. Is that right? No, something's gone wrong. Where are we? Couldn't match expected to IO char. Where am I? Oh yeah. I want to read file, word file, of course, to get something of type IO, not word file itself, which is a string. Okay, let me just see if I can actually get a random word. Consolidate. It's a nice random word. Another random word, non-corrective. Loverhood. Don't know that word. Okay, I was surprised last year when I did this that the words really can be quite scary. It turns out that it's actually a full web second edition dictionary that the Mac has in its word list. So it's a really monster word list. So it's pretty good for this game. If you like.
The longest word from the dictionary.
Yeah, the longest word. Yeah. Okay. Any questions about that? Okay, so that involved doing some other I/O stuff. Wasn't central to this course, but that was the simplest way we could generate a number in the appropriate range in order to pick a random value from the list. Let's get back to the game loop. All right, so when have we won the game? What is the condition? Can anybody describe in words roughly when we've won the game? What does it take to win the game? Yeah, or yeah, roughly speaking, when your guesses contain the same characters in the word. Well, actually, what it is we need to check. Let's start writing a list comprehension. We're going to look at all the characters in the word, and we want to check whether each one of these characters is contained in the list of guesses. Okay. So how do we test whether a character is contained in a list? Well, we could write a definition for that. But you can well imagine this is a pretty common operation. Given a list and a thing, asking the question, is the thing in the list? Okay? That's a job for Hoogle. We have a thing, and we have a list of things, and what we're asking is whether it's in the list or not. Okay. Are there any other constraints on the type? Well, we can't do this for any old lists. We can only do this for lists of things where we can compare for equality. Is it equal to the first? Is it equal to the second? So there's a constraint on this which will help the search, although probably you'll find it without the search. We're looking for something of that type. And sure enough, the function lm, short for element, is a list membership predicate. I'll read this to you, it's rather small, usually written in infix form. You can ask when an element, something is an element of a list. So you can ask whether 1 is an element, or 1 is an element of the list from 1 to 10, for example, and the answer is indeed true. So we can ask whether C is an element of the guesses G. Now this produces a list. All of those things have to be true for this to be a win. How do I test whether all of the things in this list are true? The function AND. Big AND, rather than the AND operator. Okay, so that will tell us whether we have a a win. And if we have, we can, let's just keep this short for the moment. We have a win. Well, probably it's good to display what the word is. The word was W. Okay, W here is the W from the game loop, which is in scope, and G is the guess. Okay, any questions about that? Now, actually, it turns out that there is another operator predefined, which is a way of testing whether all of the elements of a list satisfy a given property. So it's a function called all. So we could have written this as all of these things should be an element of G. So that would be another way of writing this definition, using another of the predefined functions. Okay. When have you lost the game? Say again? No, guess limit is a constant. Guess limit never changes. It's a functional program. Yeah, when the length of guesses exceeds guess limit, roughly. Right. I mean, if I have a guess limit of 10 and I have a 12-letter word, then I'll never guess it. If I count the good guesses, so I only have to count the bad guesses. So I want to take the guesses and I want to throw away all the letters from the guesses which are in the word. So I need to take the guesses and throw away things which are in the word. And there's a built-in function for that as well. And I won't go through the job of looking it up. But it's the list difference operation. That's that operation. That'll take... So if I take, for example, the list from 1 to 20 and take away the list from 10 to 30, what will I get? Well, I'll get the list from 1 to 9. So I can't take away things that aren't already there, but I can take away the things that are there. Okay? So this is the list difference operation. I can use that. So this is the number of things which are, the number of lives that I've lost. So actually what I'll do is I'll calculate the lives. It's rather handy to have the lives, and that's max, what was it called? Max guesses? Guess limit, sorry. The lives will be the guess limit minus the length of the list of the number of guesses where you take away the good guesses. So when you lose, that's when your lives are less than or equal to 0. All right? So we calculate how many lives we've got left, and we lose when the lives are less than or equal to 0. And let's do that here. We're going to okay. All right, let me just get this to compile. I've got an I/O thingy problem. Oh yeah, sorry, I haven't put my brackets in. So I need to put a bracket around this because the function application binds more tightly than the operator. So one way of fixing that is to put in a low precedence function application. The other way is to put brackets around the whole thing. Okay, any questions? All right, maybe we can actually run this thing. How far does it go? Type star, okay. Actually, now it's a random word, but I actually have no idea how many letters are in the word. It's not going to be very good, is it? I lose. The word was temptable. Okay, so what's missing here? Well, I need to actually show the status. And I've got at the moment just type stuff. So I obviously need to show the progress so far. So I need to do some more things than just type your guesses. How many lives do I have left? I can reuse this guy up here. I can show that. That's how many lives I have left. Okay, so now I've got a nicer message, but now I actually need to show, in addition to that, I want to actually show the progress so far. I need to show the parts of the word that I've guessed. Okay, so what do I need to do? Well, I need, for every character in the word, for every character that's found in the word, if the character is in the guess list, I'll show the character. If the character is not in the guest list, I show the underscore. So if the character is an element of the guest list, then I'm going to show the character. Otherwise, I'm going to show the single character underscore. Okay, so this now is a string, a list of characters, which I should print on the screen using the same function. So this will display the guess so far, and this will then give me some more information. Let me try that again, and let's have another go at main. It takes a little while here. I think the main time in the computation to get started is actually calculating the length of this file. If we actually predefine the length, it'll be quite a lot quicker. Okay, I've got 10 guesses, 10 lives remaining. I can type EAST, they're always good. Oh, that looks good. And, oh, it already looks like a hard word, doesn't it? It's got to have a P in it. No, it hasn't got a P in it. Okay. Obviously. Yeah. Nice. Okay. I'm missing, so I've got a question at the back there.
When you find win,
yeah.
you write and before the list where you see elements G, all that. Why don't you do that when you do the do clause in with string line? If see elements.
So say again, when I wrote.
You put and when you find win, just under the.
Yeah, yeah. I put end. Did you say?
Yeah. Up 2 rows, 3 rows.
Here.
Yeah.
Aha.
List there.
Yeah.
Why don't we do that
on this one here?
Yeah.
Well, so win is a boolean. Win is a boolean guard. It's going to tell us whether I've won or not.
Yeah. So
that needs to be a boolean value. I convert a list of booleans into a boolean using the and function. What I want here is a string. So I can't apply and because it'll change the type into a boolean. That won't be any good. Okay. Okay, there is a bug in this. Let me show you what the bug is. I can. There's an attack on this. Yeah. So what's going wrong here? It allows me to guess as many as I like. So however many guesses I make, it accepts them. But how many guesses should it allow me to make?
Less than the remaining. Equal to.
It shouldn't let me guess more than the number of lives I have left, right? So I can fix that really easily. I can take the lives from the guesses. That is to say, I shorten the number of guesses to be equal to the number of lives at most. Okay, that fixes that. There's another problem, which is maybe just a kind of nastiness in the game. It doesn't. Let's suppose I try guessing Q. If I guess Q again, it counts it again, even though I've already guessed it. That's not very nice. That's something we can fix over here. We're adding characters even if they're already in the list. So how do we add characters without adding extra ones to the list? Well, we can be kind by using a more set-like operation rather than a list operation. And there's an operation called union, also in the data.list, which will add any elements found here into this, providing they're not already there. So it never adds duplicates. So this will prevent G from having any duplicates. So if I compile that one again, I can run that again. If I guess CD, for example, huh? What happened there? I thought I'd just fixed that.
Maybe intersect instead of something like that.
No, I want to increase the number of guesses that I have. I just don't want to increase it. So if I have 1, 2, union 1, 2, 3. Let's say union 1, 3. It will add the 3, but it won't add the 1 again because the 1 is already there. It didn't work.
Reload the file.
Did I reload the file? Probably not. Ah, I didn't reload the file. It's always good to reload the file if you're trying to debug it. Yeah. All right. I believe we've got a complete game, and I don't think there are too many bugs left in it. And we've done that just in time. So what we've seen today then is our first taste of do notation here with I/O. It turns out, interestingly, that do notation is not just about commands for interacting with the operating system. It's actually something which is polymorphic. There are many types of commands. They're all called monads. I/O is just one example of a monad. Next week, we're going to look at another example of a monad, another kind of command. Today we've seen commands for interacting with the operating system, I/O. Next week we're going to see commands for building random generators for quick check. Quick check needs to generate random values in order to do testing. If we're going to generate random values for data types that we've defined, we need to tell quick check how to do that. The way we're going to do that is using commands like this, but not of type I/O, of a type specially for quick check. So we're going to see a similar style of programming, but for a very different kind of instructions. Instructions for generating random things, and not instructions for interacting with the operating system. The difference will be instructions of type I/O interact with the operating system. The instructions that we're going to use next week will be the instructions that are run by quick check in order to generate random values. Any other questions before we close for the day? Okay, thank you very much.